Hi, thanks everyone for joining today. Today I'll tell you a little bit about some of the work that we're doing on designing equitable risk models for lending and beyond. This talk is in two parts. In the first part, I'll discuss some common mathematical definitions of algorithmic fairness, and I'll argue that these are often at odds with important understandings of equity. Now, in the second part, I'll have a little bit more of a positive message and argue that while these mathematical definitions don't always give us what we want, we can still design more equitable systems by explicitly separating prediction from the decision-making itself. So let's dive right in with the first part, assessing bias in risk models. So statistical models of risk are now used in a variety of domains in finance, medicine, criminal justice, and beyond. And these are often used to drive these high stakes decisions, to inform high stakes decisions. And one of the most important questions that we have about these models is, are they fair? And we don't even understand exactly what fair means. That's part of what I'm going to discuss. But at a high level, we're concerned about whether or not these models are broadly fair or equitable. The motivating example that I'll be discussing in the first part comes from criminal justice, but many of the ideas that I'll talk about apply almost unchanged to all these other domains as well. In the second part of the talk, I'll talk a little bit more specifically about financial applications. So in the criminal justice system in the US, shortly after someone is arrested, a judge has to make a high stakes decision about whether or not to release or detain that individual while they await trial. Now, the goal is to balance flight risk and public safety on the one hand with the financial and social burdens of bail on the other. So this is a complicated task. It requires a prediction, and often this is done informally, but more and more we see that in jurisdictions across the United States, judges are incorporating what are called risk assessment tools when making these types of decisions. So these are statistical tools that assess the likelihood. Often they look at two different outcomes. They assess the likelihood that an individual failed to appear at trial or alternatively commit a future crime while they are out on bail. And we call this a defendant's risk of FTA, or failure to appear, or criminal activity. So these risk assessment tools are often pretty simple. So here's a real one. It's used in many jurisdictions across the United States. It's just a weighted checklist. It's based on 4 factors. And here's a hypothetical individual with no pending charges, 2 prior convictions, 2 prior missed court appearances in the last 2 years, and no prior missed court appearances before that. These missed court appearances are called FTAs, failures to appear. Now, if we just add these factors up, what do we get? We get a 5 out of a possible 7 points, and we might choose to call this individual quote unquote high risk. So this is it. This is all that these types of risk assessments look like, or what common risk assessments look like. And now there's one question of whether or not these are accurate, and a related question is whether or not these things are fair, equitable. So a few years ago, this question really got a lot of attention, in part because of this article that came out in ProPublica, and the title pretty much says it all: machine bias, or software used across the country to predict future criminals, and it's biased against Blacks. So this is the question that I want to interrogate, or the claim that I want to interrogate in the rest of the first part of this talk. How can we understand whether or not an algorithm, the specific algorithm, but also more broadly, these types of risk assessment algorithms or predictive algorithms are fair? So in one of the big claims that I'll be making is that while there are a variety of mathematical measures of fairness, almost all of these are poor proxies for detecting discrimination. And even worse, attempts to satisfy these formal measures of fairness can quite perversely lead to discriminatory decisions. So not only are these mathematical definitions not helping us in many cases to detect fairness, they also, if we take them seriously as design principles, they can lead us to create discrimination where there otherwise might not have been any discrimination. So these are pretty strong claims, and so I'll try to argue these in the context of 2 specific examples. So the first is a mathematical definition of fairness that we call classification parity. And just as a side note here, there are many different names for some of the definitions that I'm going to talk about here. This field is still maturing, and so we haven't sort of collectively come upon a common language. So what I'm going to call classification parity, you may have seen under different names. And so very broadly, what does classification parity mean? It means that an algorithm is considered to be fair under this definition if error rates are approximately equal across groups. And in this case, just for concreteness, I'm going to consider groups defined by race. And even for even more simplicity, I'm going to consider two groups, white and black individuals. So this definition of fairness is quite popular, and it's already made its way into some proposed legislation. So here's sample legislation from Idaho last year. And so this was some of the language in an early version of the bill. Pretrial risk assessment algorithms shall not be used by the state until first shown to be free of bias, meaning that an algorithm has been formally tested and the rate of error is balanced between protected classes and those not in protected classes. So again, this is capturing the idea that this quite intuitive idea, let's say, that an algorithm is fair, is considered fair if error rates are approximately equal across groups that we care about. Also, just to clarify, this requirement is eventually removed from the final bill, in part for some of the reasons that I'll discuss next. So there's one question before we really dive into this, is what does it mean to say that error rates are balanced? We have to define, we have to pick a specific measure of error rate. And again, for concreteness, I'm going to pick one popular measure, the false positive rate. This is the one used by ProPublica, but almost all of what I'm going to say next translates to a variety of error rate measures that you might consider. So just to remind everyone what the false positive rate means, specifically in this example of pretrial criminal justice decisions, the false positive rate says among individuals who did not ultimately go on to reoffend, what proportion of them were deemed high risk by the algorithm. So this is a false positive. The algorithm said this person was high risk, but in reality, they did not go on to reoffend. So again, what is false positive rate? Among people who do not go on to reoffend, what proportion are deemed high risk by the algorithm? So in Broward County, we looked at some specific data, and this is the same data that the ProPublica journalists looked at. And what they found is some quite striking statistics. So among Black individuals who did not reoffend in Broward County, about 31% were deemed high risk of committing a violent crime. And likewise, among white defendants who did not ultimately go on to reoffend, about 15% were deemed high risk of committing a violent crime. And so these statistics are quite striking. We have a false positive rate of 31% for Black individuals versus 15% for white individuals. So the false positive rate is large both in a relative sense, about twice as high, and also in an absolute sense, about 15 percentage points. This is quite large gap. Now, what I'm going to argue is that while this might feel viscerally bad, and honestly, the first time I saw these statistics, I also thought, oh, there's clearly something wrong with the algorithm itself. What I'm going to argue now is it's actually a little bit more subtle than that, and that our intuition, or our first intuition when looking at these types of statistics, can be quite misleading. So I'm going to do this in pictures. So here is a caricature of two populations. We have our blue population and our orange population. And underneath each of these stick figures in both the blue and the orange population, we have numbers indicating the risk of reoffense. And for right now, let's just assume that these are perfect estimates based on the data that we have available to us. These are perfect estimates of risk. So we know that one individual is 10% likely, another is 50% likely, 70% likely, et cetera. And again, I'll come back to the extent to which these estimates can be treated as perfect given our data. But for now, just for simplicity, let's imagine the situation where we actually know, given the available information in front of us, any individual's risk of reoffense. So that's what these numbers are under each of these figures. The other important point is that in any two groups, in the blue group and the orange group, or in any two groups, we expect the distribution of risk to be different between those two groups, not necessarily because risk is different, risk is inherently distributed differently across different groups, but because groups might be it might be in different environments, and those environments might affect one's risk. And so what I'm drawing here is the outcome of all of these complicated factors that just boil down to a risk score for any individual, and those risk scores are distributed differently across individuals into different groups. And the third important feature of this example that I want to point out is that there's this dashed line right in the middle, and for simplicity, we're going to assume that two actions are taken depending on what side of the line an individual lies on. So to the right of the line, we might say that an individual is detained. To the left of the line, we might say that that individual is released. And importantly, those decisions are irrespective of the group in which an individual is in. So I just draw that line, in this case, right at 50%. Irrespective of the group that someone is in, I make the same decision conditional on their risk score. So in that sense, these you might consider these decisions to be equitable, to be fair, in that they only consider risk, they don't consider anything else about group membership. Okay, so now with this setup, let's consider false positive rate. And for simplicity, let's first do this in the blue group. So what is the definition of false positive rate? Again, this means that among individuals that did not go on to reoffend, what proportion were deemed high risk? So let's just do this in pictures. So here we have our probabilities of reoffending underneath them. Some of them in red actually go on to reoffend. And so we can count the ones that don't go on to reoffend. These are the 6 blue figures in this diagram. And then we say, among those that did not go on to reoffend, what proportion were deemed high risk? And these are just the 2 blue figures to the right of that dashed line. These are the ones that are deemed high risk. Okay, so in this case, we have 2/8, or 25% false positive rate. So now let's do the exact same thing for our orange group. So here, this orange group is a higher risk group. And so we have more, we can see this distribution shift to the right. So more people on average will reoffend. That means fewer people will not reoffend. That means the denominator in our false positive rate is smaller. And the way I've drawn this figure, among those who do not go on to reoffend, more of them will be deemed high risk. More of them are to the right of this dashed line. So we have a figure like this, where on the bottom we have 6, and on the top we have about 2.5. And if you work this out, it's about a 42% false positive rate. So again, just summarizing here, we have these 2 different groups, the blue group and the orange group. And even though we've drawn this line so that it doesn't consider group membership, we're making the exact same decisions for everybody in the group, conditional on that risk score itself. And so in this sense, it's a broadly fair, equitable, it's an algorithm. We still see dramatically different false positive rates. So in this blue group, we have a false positive rate of 25%, versus in the orange group, we have a false positive rate of about 42%. So this is what's called the problem of infra-marginality. And the issue is that while we intuitively think of fairness, or in many sort of legal and social contexts, we think about fairness as not having a double threshold of applying the same standard to all individuals. The false positive rate is is an inframarginal statistic. It's not only capturing information about what's going on right at that threshold, but it's also based on information in the tails of the distribution. So it cares not only about the threshold, which is where intuitive ideas of fairness lie, but also what's happening on the entire distribution. So again, in this case, the false positive rate is not closely aligned with many legal, social understandings of fairness. And so looking at the false positive rate statistics themselves can give us a misleading picture of what's going on at the threshold. Now, if we look back at the real data, what we had just been looking at is a stylized example, but if we look back at the real data, we do see that a phenomenon like this seems to be occurring. So here we have the risk distribution, the estimated risk distribution for white individuals and Black individuals in Broward County. And you can see that there's this heavier tail for Black individuals in Broward County relative to white individuals. And if we believe these numbers, if we believe that these are the actual risk estimates, legitimate risk estimates given the data available to us, then this would explain where these false positive rates, this disparity in false positive rates are coming from, even if we were to draw this single threshold and make these risk classifications independent of group, conditional on the risk estimates alone. So now you can ask, well, okay, so maybe mechanically the false positive rate is explainable in a sense by looking at differences in risk distributions, but we can still be unhappy that we're saying that even if we apply the same threshold, we're still doing something wrong, that there's still a harm that one group is facing relative to another, even if in a sense this is explainable or justifiable by differences in risk distributions across these groups. It still might feel like there's something fundamentally wrong with this way of thinking about the problem. So I now want to push back on that intuition and argue that in fact there's a much deeper issue here, and that once we understand that these risk distributions are fundamentally responsible for driving our false positive rates, then that leads to all sorts of perverse outcomes. So let's go back to our orange group. Now remember, this was the high false positive rate group. This was the group with higher risk on average, but we might be concerned about that if we were to draw this threshold, then we're subjecting them to higher false positive rates, and in turn might be causing harm to this specific group. Okay, so how do we lower the false positive rate for this orange group? Well, one thing that we can do is we can go out and arrest a bunch of college protesters. Now, of course, I'm being facetious here. We're not going to go out and arrest a bunch of college protesters and pretend that we're making this group better off. Clearly, doing this is making the group worse off. But what's going to happen mechanically, mathematically, when we do this? If we arrest a bunch of college protesters and we accurately recognize them as low risk, what happens to our false positive rate? Well, most of these low-risk individuals, they go into the denominator of our fraction when we're computing the false positive rate. None of them are flagged as high risk, so our numerator doesn't change, and we end up lowering our false positive rate. So we went from a situation like this, where we saw these gaps in false positive rates between the blue group and the orange group, and we might intuitively viscerally feel that this orange group was being harmed because of this higher false positive rate. All of a sudden, we go and we arrest a bunch of college protesters, and what have we accomplished? We have now equal false positive rates, and it looks like everything is great. Now, of course, the point isn't an incentive issue. It's not that we say, if we were to require equal false positive rates, then all of a sudden decision makers are going to start arresting people and trying to mess with these statistics to make it come out one way or the other. That's not the point that I'm trying to make. The point is that we need to understand the distribution of risk itself to understand where these false positive rates are coming from. So if I just were to show you this picture, and I didn't tell you that how this picture was derived, and you just saw these false positive rates at 25%, you might think everything is great. But if I just show you this picture, which is objectively better for the orange group, more equitable for that orange group, you might come to a completely different conclusion. And the point is that we are, by focusing on the false positive rate itself, we're missing all the distributional properties that are important when understanding equity. Okay, so now I want to talk about a second way that we can formally conceptualize fairness, and this is through what's called anti-classification, or one name for it is anti-classification. And this is arguably the first thing that somebody might say if you ask them, how do I know if my algorithm is fair? The first thing they might say is that intuitively, a fair algorithm shouldn't use protected class. So it shouldn't explicitly depend on race or gender. And a quick retort to this is, sure, this is a low bar. But in fact, it's such a low bar that it really doesn't tell us anything, that we know that it's possible to discriminate even using these blind policies that don't explicitly use race or gender. So redlining in financial services is a common example of this. And so we may say, okay, this is a low bar. Of course, we don't want to use protected attributes when we're making these decisions, but we want a lot more. Now, what I'm going to argue, in fact, is that anti-classification is not just a low bar. In many cases, we actually want to use the protected attribute itself for improving our decisions. And if we don't use these protected attributes, again, somewhat perversely, we can end up discriminating against the very groups that we're hoping to protect. So let me illustrate this with an example. Back to Broward County. Again, this is based on the data that we have. Women are less likely to reoffend than men of the same age with similar criminal histories. And so conditional on the sorts of things that are typically used when assessing risk, women in Broward County are less likely to reoffend than men. And again, this is a property that I'm going to show you data from Broward County, but this is a phenomenon that we see all across the country in different jurisdictions. So what do we have? So again, this is the real data. So on the horizontal axis, we have COMPAS score. So this is a particular risk score that's used in Broward County. And on the vertical axis, we have the empirical recidivism rate. And we can see for any given risk score, based on these gender-blind risk tool that's used in Broward County, women are less likely to recidivate than men, conditional on that risk score. So now let's say we make a decision. Let's say we make some classification and we say everyone who's above 8 is going to be deemed high risk. Everyone who's below 8 will deem low or medium risk. Now, what's going to happen here? Well, the women that are right at that cusp of high risk, they're actually the same as men that have that score of 5.5. And so the women who are right, who we're calling high risk, are really the same objectively as the men that we're willing to call medium or even low risk. And again, why is this the case? It's because we haven't used gender in making these assessments. And so based on criminal history, based on age, based on the factors that traditionally go into these risk scores, what we're seeing is that we're systematically underestimating risk for women and systematically overestimating risk for men. And we end up with this perverse situation. So again, the punchline here is these gender neutral models, these gender blind models, can in fact lead to discrimination. And there's statistically a very easy fix for this problem. You just include gender in your model, or another way of thinking about this is you fit one model for men, one model for women. And if you do this, then you're not going to have the problem that I just described. And in fact, some jurisdictions do this. Wisconsin, for example, is using gender-specific risk tools in informing decisions. But of course, we still have this complicated issue now of, do we want this? And there's this perception, in this particular case in the criminal justice system, there might be this perception of two justice systems, one for men, one for women. And even if statistically this might make sense, we have to worry about perception of equity in this particular decision-making process, and it's unclear what the right thing is to do. And so I don't want to say that we definitely should be using group-specific algorithms in all these decisions. I think these are complicated problems, and we do have to think carefully about what's happening in any given instance. But I do want to point out that the intuition that the even idea of using group information when constructing risk assessment tools, that itself can be quite problematic. So now I want to end this first part of the talk by going back and talking a little bit about bias in the data. So this first part, I've been hinting at, or very explicitly talking about, some of the issues with our formal definitions of fairness, both in terms of classification parity and in anti-classification. And the idea here is, the way I set up the problem is, let's assume all our risk estimates, all our data, everything is perfect. We're in this great world. We believe our predictions. Even in this great world, we still have these issues that these common heuristics don't use group characteristics when making predictions. Look at false positive rates, look at error rates when trying to decide whether or not an algorithm is fair. These common heuristics can lead us astray. But I haven't really talked about what if the data themselves are biased. So I at least want to touch on this issue. So the shorter answer is that if you have biased data, I think there's no reason to believe that all of a sudden these formal definitions of fairness are going to get you out of the problems of biased data. But at the very least, we should recognize some of the ways in which the data can be biased and can lead us astray, aside from the mathematical formalizations of fairness that we've been talking about. Okay, so what is the arguably the most important way in which bias can impact our decisions is what I call bias labels, also called measurement error in the statistics community. And here, the idea is that these are predictive algorithms, and ultimately, what we want to predict is something like the probability that an individual will commit some future crime, but what we actually predict is the probability that an individual will be observed or reported committing that future crime. So to the extent that there is a disconnect between the proxy and the actual construct that we are seeking to predict, these estimates can be systematically biased. So one example in the criminal justice system where this is the case is for low-level street crime. Think of outdoor marijuana use. And so even though we know that from surveys and other sources, we have strong reason to believe that minor drug use is similar across race groups. Who is actually arrested for drug use? This is often Black and Hispanic individuals. And so again, what we ultimately care about in that example is who is likely to participate in drug use. If we train an algorithm that is based on arrests for drug crime, then we're going to get highly skewed estimates that systematically overestimate use for Black individuals and underestimate use for white individuals. And another example, in admissions, we can consider the St. George's Hospital in the UK. They developed an algorithm to sort medical school applicants. The algorithm, perhaps reasonably, or perhaps understandably at least, was trained to mimic past admissions decisions by the human decision makers. But what went wrong in this case? The past decisions were biased against women and minorities. And so all the algorithm did was codify this discrimination in the system itself. So again, this is this issue of proxy discrimination, where what we seek to estimate in this particular example is something like who would be successful if admitted. What we're actually ending up predicting is who would have been admitted by previous human decision makers. To the extent that those are misaligned, in this case, they're misaligned in the sense that human decisions were discriminatory. We're just baking that discrimination into our algorithm itself. So we have to be very, very careful about making sure that we're predicting what we actually want to predict. And ultimately, I think this is quite hard. So it's not, I think it's useful to understand that this issue can arise. Circumventing it in real world examples can be quite difficult, but it's at least useful, I think, to understand where this is coming from. Okay, so that concludes the first part of the talk. And the message, admittedly, was a little bit, perhaps a little bit depressing in this first part, that I was arguing, and the quick recap is I was arguing that many of the ways that we think about algorithmic fairness suffer from these fundamental issues. And so they're quite natural, thinking about balancing error rates, thinking about removing group characteristics from the decisions themselves. They feel very natural. In many cases, they really don't work. And not only do they not work, they can make things worse if we use those as a design principle. So I don't want people to tune out right now. So this is the important part of the talk, where I am going to try to advocate for a more positive message that we can, with some work, we can design better, more equitable algorithms. Not easy. but I think we can do it. And I would say that sort of a side comment here is one of the reasons that I think these mathematical definitions of fairness have become so popular is that they are easy. Is that we can say we can run this suite of statistical tests. We can design our algorithm. We can say this is fair, this is not fair. We audit it. It's relatively straightforward. We just get this like scorecard. It says here's my false positive rate. They're equal across groups. I can go home and rest easy, knowing that I haven't created a bad algorithm. Now, that's great, and unfortunately, I don't think that applies in many situations. And so even though it's easy, it's not actually getting us what we ultimately want or what we need in many applications. And so the second part, I'm going to, again, try to get us to a point where we can design more equitable algorithms, but I want to flag right up front that this isn't going to be easy. This isn't going to be simply run this suite, run this battery of tests against your algorithm, and then everything will be good. It's going to be a lot more difficult, but I still think conceptually it'll help frame the problem. And I think fundamentally there isn't a way to get around some of these issues, these complicated issues that I'll be presenting. Okay, so what is the high-level message? The high-level message is that algorithms are not policy. And so one key design principle is to separate risk estimation, prediction, from the policy decisions themselves. And why is this? Well, statistical algorithms are good at synthesizing information. They're very good at estimating risk. But we still have to set this equitable policy. Even if I give you the perfect risk estimates, we don't know what to do with those risk estimates. Going back to this criminal justice setting, that we might, again, if somebody hands me these perfect risk estimates, well, one thing we might do is we might decide to detain people who are relatively high risk under this algorithm and release people who are relatively low risk. The other thing we might do is just simply limit money bail for all individuals and consider non-custodial interventions. We might say that, yes, this person is high risk of failing to appear at their court date, and so what are we going to do? Instead of locking them up, we're going to figure out why they're high risk and address that issue. And so maybe someone is high risk because they don't have a good way to get to court, and so a small intervention like providing them with transportation benefits could help get them to court, and all of a sudden we reduce that risk and improved that particular individual's life. So for a small cost, we can have much better outcomes. Again, in the financial sector, we might offer support services for individuals to change one's risk profile. So traditionally, what might we say? We say, oh, this person doesn't appear to be creditworthy. We're not going to extend credit to them. Alternatively, we might say, this is why, this is what we think the issue is, and we're going to help improve that particular person's likelihood to repay, and then we might have better outcomes. So again, the policy itself is not determined from the risk estimates. And so this is the high level point that I want to make, and I want to play this out in a specific example that gets into this in more detail. Okay, so I want to do this in the financial context, and the motivating fact is that we have these quite striking inequities in lending. So about 20% of US households have no mainstream credit, meaning they're not eligible for small dollar loans. But about 3 in 4 of these households stayed current on their bills, their household bills, so think electricity bill, in the past 12 months. And so many of these individuals, even though they're not traditionally eligible for small dollar loans, they're in fact probably quite reasonable candidates for paying back these loans if they were given the chance. Now, to make matters worse, many of these households are disproportionately Black and Hispanic, and so the broad question we want to ask is, how can we design a more inclusive lending policy that's addressing this gap, this inequity in the current system? So the challenge in a more technical level is that we want to allocate our resources to these underserved groups, so again, think individuals without mainstream credit, while remaining relatively efficient, meaning giving loans to those who are most likely to repay. So these are 2 design goals. So let's again think about this in terms of pictures. So we have our blue group and our red group. And here the way that I partition these groups is in terms of banked individuals and unbanked individuals. The banked individuals are those who we know quite a bit of information about. The unbanked individuals are people we don't know that much information about. And if we just sort of line them up, if we kind of score them, we line them up on the spectrum, we have a few different facts I want to point out. The first is, on average, these banked individuals are more likely to repay, meaning they're shifted to the right on this line. The blue individuals are shifted to the left on this line on average. The other fact that's important in this diagram is that the blue individuals tend to be clustered, so we don't know that information about these blue unbanked individuals. We can't really separate them out that well in this particular example, so they tend to be clustered right around this sort of low, medium risk risk part of the spectrum. So now, how might we traditionally make lending decisions in this case? We might pick a threshold and give loans to people to the right of that threshold and deny loans to people to the left of that threshold. Okay, so this, it might make sort of narrow financial sense, but if you look at this diagram, what's happening, all the loans are given to these red individuals who are banked, and all of the blue individuals are denied loans. So we might not be happy with this. So now, one way of improving the equity in this particular situation, and we can just have two thresholds. So we can say, yeah, we want to give these loans, and we understand that we have different risk profiles in these two different groups. And so we might say, okay, let's give some loans to these high, these low risk, high likelihood to repay red individuals, and we'll also give loans to these highest likelihood to pay blue individuals, even though in an absolute sense, there's still lower likelihood to pay than some of the red individuals that we're not giving loans to. So again, all we're doing here is applying two different thresholds. This is one way that we might be able to improve the equity of our decision-making process, giving the information that we have available to us. So now, this is sort of, I would say, reasonable, and it highlights one of the inherent tensions that we're not going to ultimately be able to get around in this type of problem, that if we want to distribute resources to an underserved group, then there's going to be some cost to that. That's just in many cases, that's something we can't avoid. There is going to be this trade-off between total equity or total utility and equity in the sense of distributing resources to a group that wouldn't otherwise receive those resources. Now, what I want to present is a simple strategy just to build intuition for reducing some of this trade-off by selectively screening, by selectively gathering information on some individuals. So in this particular case, we're imagining that it's costly to examine someone's household bills. It requires time, it requires money. And so we don't want to do this for everybody. We want to strategically figure out who do we want to gather more information on, and then based on that, make more refined choices. Okay, so again, here we are in this basic scenario. Let me just build some intuition for you. So we have our red banked group and our blue unbanked group. Let's say we can get information on everybody. Well, it might happen in this blue group. Well, in the red group, nothing really changes. We already have a lot of information on them, so nothing really changes. But in the blue group, this group that we didn't have a lot of information on, if we went in, if we invested and tried to get more information on them, all of a sudden we might split this group up so we can tell in this blue group who is higher risk and who is lower risk. And now, given this distribution, we might draw a single line and say, okay, now we're going to give loans to everybody above a specific threshold, or alternatively, we might say, again, even though we have this better information in the blue group, we still might set two different thresholds to help to improve even further the number of loans that we're giving to this underserved group, the blue group, in this particular example. Okay, so now, so that simple example, we were assuming I could just get information magically for free on everybody. But really, in the real world, this is costly. We can't do this for everybody, and so we need a way to do this strategically. And some of our work has developed. In some of our work, we've developed a very simple statistical method for selecting a subset of individuals to screen to get more information on. And I'm not going to go into the details, the technical details on how we actually do that, but informally, what we do, we want to screen individuals close to the threshold. We want to screen individuals who we might plausibly make a different decision for if we were to get information on them. So the trick here is appropriately defining what close is. We do this in the form of a constrained optimization that we can write down and then solve. But I won't get into the details. I'll show you a reference at the end of the paper that you can look at for the details. But right now, I just want to give you this intuition and then work out a simple empirical example. So to show you how this might work, I'm going to look at I'll do a simulation on this well-known German credit data set. So this is a quite stylized simulation, just to give you an idea of how this might work. So here, for concreteness, I'm going to look at 1,000 individuals, 70% of whom are creditworthy, and we're going to consider two groups: those who own a residence and those who do not. We have those who own a residence, we have more information on, and we also know that they're more creditworthy in this particular data set. And so we want to provide more loans to this underserved population of individuals, hypothetically in this example, of those who do not own a residence and who might not have as much access to mainstream credit because of that. Okay, so we're also going to assume, and in this particular example, that the cost of screening is about 10% of the loan amount. And so again, you can imagine that these loans are about $1,000. These are small dollar loans, and we're paying about $100 for additional screening. Okay, so what's going on? How do we think about the trade-offs in this particular example? So if we do this simulation based on those parameters that I just described on this particular data set, first we can do this without any additional screening. So what is going on in this plot? On the horizontal axis, we have how much utility is being assigned to this underserved group, so this targeted group of individuals that don't own their own residence. So we might want to provide more loans to this group. So this is telling us how much we're assigning to that group. And on the vertical axis, this is the total utility that we're getting. So you can think of this as the total number of loans that we're able to distribute. And so now we have this kind of classic trade-off here, is that if we want total utility, what does that mean? That means, in this particular example, the way this is set up is that we're going to have actually zero utility for this targeted group. And as we increase the amount of utility that we provide to this targeted group, we lower our overall utility. And so there's this trade-off between being equitable in the sense of providing value to this underserved group and being overall efficient in the amount of total utility that we're able to provide. So there's this decreasing function here. And what I've drawn here is a Pareto frontier, saying among all of our allocation strategies, these are the best that we can do. And this is illustrating that trade-off without any screening. So now, if we actually were to implement screening, what's going to happen? Well, in this case, it flattens that curve. It flattens this trade-off. And so we don't have as stark a choice to make between how much utility we allocate to this targeted group, this underserved group, and how much utility overall in the system we're generating. And so by selectively collecting information on individuals that information might make a difference for, so doing this in a strategic manner, we're actually able to lessen this trade-off, not remove the trade-off. And again, I think in most of these types of important examples, I don't think there's a free lunch here, that there is this trade-off, and this is the sort of fundamental tension in designing equitable policies, is that we have to grapple with this trade-off. And so we can't get rid of it in most of these important cases, but we can alleviate it. We can flatten this Pareto frontier, which helps improve our decisions. Okay, so now that concludes the sort of technical part of the talk. Just want to wrap up with a couple thoughts. So the first is that equitable decision making generally requires examining this trade-off concretely between these competing concerns. And so how much utility do we ultimately want to allocate to a particular group versus how much utility overall in a system do we want to allocate? This is a fundamental tension. And so, in many of these situations, we can draw out this curve, but we don't know where we want to sit on that curve. And that is that decision that the policymaker has to make. So best case, in many of these cases, we can draw the curve, but statistics isn't going to tell us where we should sit on that curve. We have to make that policy choice. So there is this fundamental tension. And this is a fundamental tension that is not captured by traditional measures, mathematical measures of fairness, where we might say that there's a tension between different mathematical formulations, but they're not actually getting at the key policy choice, or at least in my view, they're not actually getting at the key policy choice that we have to make, which is how much do we want to allocate to different groups. This is the equitable side of the equation versus how much utility do we ultimately want to allocate to overall in the system. This is the efficiency side of the equation. Now, the second point that I want to make is that that in many kind of classic understanding of algorithmic fairness, we think of the data as being static. So we think of we getting some training data, that's it, and we have to train our models on that, and now we're evaluating the equity of our models based on the data that are handed to us. I would argue, actually, in many real-world situations, that's not our only constraint. That we don't have to say we don't have to stop at the data that somebody hands to us. We can request more data, and in the lending example, we could strategically request more information on certain individuals, and not doing so can in and of itself create inequities. And so here, again, I don't want to ground too much to that specific example that I shared, but I want to make the broader point that we want to think beyond this static world and say, what else can we do to ensure that our policies are broadly equitable? Does that mean collecting more data? Does that mean collecting more data on one group or better data on certain individuals? What can we do to make more broadly equitable decisions? So not stopping simply at the data that we have available right now, but what else can we do moving forward? So if you want to read more about this, please check out a couple of papers that we've written. The first is the measure and mismeasure of fairness. This is joint with Sam Corbett-Davies, and this covers much of the material that I presented in the first part of the talk. And the second part of the talk is much of that material is in this paper, Fair Allocation Through Selective Information Acquisition, written jointly with Will Kai, Hans Gabler, and Nikhil Garg. And so please check these out if you want to see more of the details, including the specific algorithm that we propose for selective screening. So I'll end with that. And if you are even more broadly interested in this intersection between policy and algorithmic decision making, please check out the work that we're doing at the Stanford Computational Policy Lab. Thanks for listening.